Right, so here we are going to learn about what a separable differential equation is, and we're going to learn how to solve one. All right, so let me bring in a few quick examples here. So from our understanding, an equation like this, y prime minus x squared equals y, this is a differential equation because there's the unknown function involved and there's the what and its derivative involved. It's a differential equation. Okay, and another equation, y times y prime equals x squared. Okay, so any one of these two examples right here is an example of a differential equation. However, the way how I'm seeing it, let me tackle down right into this one right here. Y times y prime equals x squared. Now, seeing this as an equation, we have our choice of specifically solve this for y prime as an expression in terms of the other variables. Okay, so let's solve this equation again. Solve this equation for y prime as an expression in terms of the other variables remaining. So that means I'm going to divide both sides here by y, making it y prime to equal x squared over y. Okay? And then that's what I arrived at. So I've solved for y prime as an expression in terms of x squared and y squared. All right. Same way with the other equation. I'm now going to solve, starting with y prime minus x squared equals y. I'm going to solve for y prime, okay, to be an expression in terms of the two other variables, of the remaining variables. So here I'm looking at adding that x squared to the other side, making it y plus x squared. Right. But now in this way right here, let me point out a property that one equation has, whereas the other doesn't. So this differential equation right here, for example, once I have solved that once I have re-expressed that to be expressing the equation as y prime equals some expression in terms of x and y, the other variables here. So I'm going to further re-express this as. That right hand side I'm going to, on purpose, rewrite that as x squared times a 1 over y. And it's all algebraically legal and approved, right? It's all algebraically legal and approved. That starting from that x squared over y expression, I purposely re-expressed that as x squared multiplied with 1 over y. Okay? And so further I realize now that this current expression here is expressing, I can now purposely isolate out just that x squared over here. I'm seeing that as some function f of x, just the x squared over here. And then the other function, 1 over y here, I can see that as another function g of y. Okay, my board space is getting a little busy right here, so it's g of y. So consequently, in the way how I'm seeing that, the equation y times y prime equals x squared can be re-expressed as y prime equal, right? And in what I did earlier, x squared times a 1 over y. But now in the way how I'm seeing it, this equation from beginning, this differential equation from the beginning can be re-expressed as a product of some function of x and another function in terms of y. That's a nature in this specific equation that I wanted to point out right here. All right, but then on the other equation, we actually cannot do that. Now, once I have rearranged the equation to express y prime as an expression that involves x and y right here, for this equation, we just can't. We're just not able to, and I don't know how, I'm just not able to express this similarly to be the similar setup as a sum function of x multiplied with some function of y. I just can't do that for this specific equation. Okay, and so now the demonstration I brought up here pointed out that some differential equations out there, we we are able to bring that into the form of y prime equal a product of some function f of x and some function f of y. Okay, whereas some other equation we can't do that. Okay, it's a special property of some differential equations out there. Okay, and so in that way, an equation like this, an equation like the one I was doing the demonstration, and I was successfully able to bring that to the form of it being a product of a separate function f of x and a separate function f of y, g of y. Okay, then that equation right here, formally we refer to that as an equation like this. Now I'm saying it has that property. I call it's a separable. Okay, it's a separable differential equation. All right, and so in that way, let's look at the formal definition of what it means by being a separable diffq on the computer screen here. All right, and so a separable differential equation is a first order differential equation that can be written in a form. So what I explained on the board here, we need to be able to express that in a form y prime on one side and equals a product of some two function f of x and g of y. All right, so now to clarify among the two equations I brought in as our quick demonstration right here to understand, to make lead into the realizing there are separable equations out there. So now the definition say separable equations at our level here gotta be the first order, and so the one I brought up earlier, y times y prime equals x. That was the initial form of that, and apparently this was a first order. And then we've seen the demonstration earlier of how it was recognized as a separable equation. All right, so in example 1 here, let's determine which one in the list of differential equations given below is decided as a separable differential equation. There may be multiple separable differential equations in this list right here, and that's why we want to check all that apply. All right, so now in this example right here, the first equation that I had on the computer screen, y prime plus y equals 3x. And this is entirely thought process, everything I'm doing here to present to anyone learning from the lesson, but think about if you're in that role, in that situation of doing it, it's completely in the thought process level right here. So I'm going to try to re-express the equation here in the form of, we have a y prime by itself. Okay, now because we all know that they all have to be first order, and so I'm going to keep that first derivative by itself, and I'm going to bring all non-derivative terms to the opposite side. So here I'm going to subtract that y to the other side. It's now minus y plus 3x. So I have first expressed y prime here as an expression in terms of the two other variables involved here, the y and the x. Okay? But then with this equation here currently that we're at right here, this expression on the right hand side or on the side opposite with the y prime notation, with the y prime variable, then we fail. With this one here, we fail to factor out, we fail to turn that into the form where it shows the product of a function f of x and a function g of y. We fail making that display. Okay, we fail re-expressing that into a product of a function of x and a function of y separately. And that's why this function here is not a separable equation. Okay. The second equation on our list that we saw on the computer screen. So now it was already in that form where we expressing y prime as an expression that involves the other variables. Okay, so we don't need to spend any effort any further efforts to rearrange that or whatsoever. And so now let's look right here. Y prime is already expressed as an expression in terms of the remaining variables. And further, I can see that. And again, as a reminder, this is completely in the thought process level right here. I can see this as, yes, clearly it's a product. And so I can see that with this product here, I can underline that now that this is some function. Think about there's some function f of x to equal x. It's a function of x separately. And then it's in a product, which now I can put a red underline brackets right here with that y. I can see that as some other function g of y right here. That is namely g of y equals y. And so now clearly this equation here does express y prime as a product of some function of x and some other function of y. This now shows clearly and helps us decide that this equation here is a separable equation. And precisely it's a separable differential equation or a separable diffie. Okay? And so this equation is considered as a separable equation. The third differential equation on the list that was shown on our computer screen previously. This equation here immediately fails being a separable. Why is that? Because there is a double prime involved here. There is a second derivative involved here. And so this is precisely a second order differential equation. So in order to be a separable equation for our class here, the differential equation needs to be a first order. And so this one here fails. And as a matter of fact, in general out there, as a generality out there, okay, then all separable equations are considered as first order differential equations. Okay. And so this is the reason why this third equation here is another one that fails being separable. And so at the end, in this entire list here, there's only this equation being a separable differential equation. All right, so now we're in example 2 over here for this lesson over here. So in this example 2, we're asked to solve this separable equation. So solving a separable differential equation in general, as a generality, means we just find the value y, or the function y, the unknown function y that satisfies this equation here. Okay, and so in this way right here, now the problem here already addressed that this equation has already been classified as a separable equation. Okay, but it's good to have a sense about what it is. I mean, it's good to be able to verify why it's a separable equation. So think about y prime here was already by itself on one side. The entire expression on the left hand side, it's completely in terms of y. Right, right here, it's some function of y. Okay? The whole thing that I put in a bracket right there is some function of y. What about some function of x? You can always you always have your choice of thinking of that as a times 1. And then 1 here, you can see that as a function f of x being a constant function. Okay, and so it's now clearly allowed me to use some illegal notation right here. So f of x is a constant term, is a constant function. But then now y prime is understood as a product of some two separate functions. One of them in terms of y, the other one in terms of x. Even though this one here is completely independent with x. But that's how we're convinced that it is a separable equation. Not only because we're trusting the instruction of the problem saying that it's a separable equation. But so now everything I have explained just now is only in a thought process level, just for any one of us to be able to verify whether the equation given is a separable differential equation. But think about in reality, this problem here is indeed given when, think about, we're in that situation where we need to solve once we have already identified, the given equation here being a separable equation. Then how are we going to solve it? How are we going to find the unknown function? Okay, so as a reminder, ultimate goal of any solving the differential equation problem here is that we have the variable y involved in our function, in our equation here, being some unknown function of x that's completely unknown. Okay, and solving means we want to find out what that unknown function is. All right, and so now upon realizing recognizing or identifying that this equation here is a separable differential equation. Let's see how we can solve this. Now, the left-hand side dy dx, we're going to rewrite it as in Leibniz notation. It's a dy dx notation. That's what y prime is for. Okay, and we learned this from calculus 1. The right-hand side is 1/2 times y squared minus 1. Okay, I'm leaving that the same for now. The next step, throughout the entire Calc 2 class, we've learned about how we can rearrange the differential. So now having dy dx as a derivative, we further understand that this is a fraction of some two differentials, dy and dx. So now I'm going to rearrange the differential dx to the other side. So making it dy equals 1/2 times y squared minus 1 dx. And so this is a skill where anyone after taking calculus 2 is very familiar with. Okay, but now further I am doing the following. I am going to divide both sides by this g of y function right here. This function in terms of y. This bracketed function in terms of y. Okay, and so this is how it looks right here. Now dividing by 1/2 means we're going to have a 2. Okay, but on the left hand side I'm going to have it's y squared minus 1. So 2 over y squared minus 1 times a dy on the left hand side, and all of that here equals dx. It's all about we are rearranging the differentials, and we are rearranging this starting equation here. First we understand the y prime by itself on one side as a dy dx symbol. Okay, and in case the main variable is used as a t or as an s or whatsoever, then it's a dy dt or dy ds correspondingly. Okay, but here what I've been doing, I was rearranging that. I rearranged, but now this step right here specifically, this process right here means I separated the variables. See, on one side it's completely all y variables on one side together with a dy differential, and then on the opposite side, right, it's all intended to be the remaining variable with the dx differential. So intendedly it was all of the dx variable in this problem right here. Right? And so now upon arriving at 2 over y squared minus 1 dy equals dx, upon arriving at that, now I'm just going to simply integrate both sides equally. We take the integral on both sides of this equation equally. And now it's produced for us two separate integrals that runs parallel. Okay, that runs side by side here. So on the right hand side it comes out as easy as just x plus c, because the integral here is integrating the function in terms of x. The left hand side here is an integral where we have rational terms. We have rational terms, and this rational term right here, we can use partial fraction decomposition skills that we've learned and mastered throughout our Calc 2 class right there. Partial fraction decomposition. We'll break this 2 over y squared minus 1 into a 1 over y minus 1 minus a 1 over y plus 1. And so on the left hand side I was still holding on to that integral because I wanted to point out that 2 over y squared minus 1 can be decomposed into the two partial fractions as written here. Okay, and the right hand side was already finished. Okay, so in that way, at this point right here, moving over to the next step right here, first term on the left hand side is going to become a natural log of y minus 1 in absolute value, and then minus second term gives me natural log of y plus 1 in absolute value, and all of that on the left hand side now equals x plus c. So here's the thing, let me clarify about the plus c here. You see, technically speaking, you need a plus c on the left hand side and plus c on the right hand side, but in the end those are just two constant terms on the two sides. So why don't we save ourselves some efforts by just subtracting all or adding them all to one side, bringing all the c's, all the constant term c's to one side and combine them into one overall constant c. That's why it's been completely legal to leave only the constant term plus c on one side, and popularly on the right hand side. Okay, so now that's how the equation at this point is reading. Natural log of y minus 1 in absolute value minus natural log of y plus 1 in absolute value. Okay, so as we have done the integrating step right here, the integration steps, and so now, but in some advanced courses of differential equation, you are allowed to see this as your final solution. However, we can actually, let me remind you, beginning goal here is that we want to see what function that is, what unknown function f of x that is, that's y equals 2. So let's see if we can algebraically make our way to this form right here, expressing this equation to the form y equals f of x. Okay, so in that way, I am not going to stop here. Property of logarithms, right? Among the properties of logarithm, we're looking at two terms being subtracted, two terms on the same natural log right here, but two separate natural log terms. And now they are in a difference. So the difference of two logarithms of same kind, we can turn that into a logarithm of a quotient. So now it's y minus 1 over y plus 1 in absolute value. And all of that here equals x plus c. Okay, and so now starting from this step right here and on, it's entirely the algebra. And so now algebraically, I'm going to rearrange this equation to make that y minus 1 over y plus 1 in absolute value to equal e to the x plus c. So the c got carried on but become part of the exponential function e to the x plus c. All right. All right, and so now on my document camera over here, allow me to bring in some algebraic details. So we're currently at y minus 1 over y plus 1 in absolute value. And all of that there was equal e to the x plus c. And so from algebra, we know that e to the x plus c is indeed e to the x plus c can be thought of as e to the c times e to the x. And that means we can see this here as a constant, as a coefficient. I mean, as a constant, and then, relative to the entire function, it's a coefficient. And so, back to the equation, I can write this as y minus 1 over y plus 1 in absolute value to equal e to the c as a coefficient times e to the x as some function. And so now algebraically, this expression inside the absolute value here, now to take away the absolute value, we've learned from algebra that y minus 1 over y plus 1 now without absolute values is indeed equal to plus and minus e to the c times e to the x. Logically speaking, now I explained earlier, the e to the c itself is only a constant, or to the whole function here, it's a coefficient. And so now even if it's positive or being a negative, it's just another constant. It's just another constant. So I have my now reason to combine all of that. I'm going to call that it's a C1 coefficient, a C1 big constant, to be either plus or a negative or a minus e to the c. Right? And so now I can write the entire equation here as y minus 1 over y plus 1 to equal some coefficient. And this coefficient C1 now could be, again, positive or negative of e to the c, and then times e to the x. All right, and so now we're going to take our time to algebraically rearrange this equation to come up with the explicit the expression of the y function right here. But now we have safely and algebraically successfully removed the absolute value signs. And so now I'm going to multiply both sides by y plus 1, making it y minus 1 to equal c1 e to the x times y plus 1. And that will make that y minus 1 equals, after distributing out the c1 e to the x to each term inside the parentheses here, I'm looking at y times c1 e to the x plus c1 e to the x. And now I'm going to rearrange, I'm going to bring that y term to the left hand side, that term involving the y to the left hand side, and I'm going to bring that constant term to the right hand side. And so now that's making it, in my next step, y minus y times c1 e to the x will equal c1 e to the x plus 1. And now on the left hand side, now I see like terms in a sense that they are all having the common factor y right here. So I am going to factor out the y, leaving it 1 minus c1 times e to the x. And all of that there on the left hand side should equal c1 times e to the x plus 1 on the right hand side. And then at this point we can easily divide both sides by the expression 1 minus c1 e to the x here to both sides, making it y equals now c1 e to the x plus 1 with over 1 minus c1 e to the x. But now that from that equation, and you've seen some detailed explanations on the document camera right there, then now that final equation, you've seen that final expression, y equal c1 e to the x plus 1 over 1 minus c1 e to the x. This is now our, what I so call this, the solution. Okay, it's the solution to our separable differential equation. All right. And so now the essential theme, the essential guideline that we can draw out from working through example 2 is as follows. Anytime we come to solving a separable differential equation, so it's a guideline. Okay, it's just a guideline right there, and it's a general instruction. Okay, but of course your equation being a separable equation, so the starting point here is we're looking at expressing our equation as y prime equals some function of x times some function of y. That's the major characteristic making it a separable differential equation. Now from this point on, the first step is to see, according to the work I've done back at example 2 right there, then we're going to rewrite that. We're going to rewrite that equation, that y prime symbol right here, as a dy dx symbol, and then making it equal to f of x multiplied with y of x, g of y. Okay, and then further we're going to now see that throughout, we're going to see that just the same experience we've been learning throughout the entire Calc 2 course, that we're going to see this not only as a not only as a derivative symbol, but we're seeing that now as a fraction of two differentials, dx, dy, and dx. So in the next step, I'm going to rearrange the differentials and rearrange the variables here. So I'm going to make that, see, now in this general form, it's making it more clear. I'm going to divide both sides by the function g of y, and I'm going to multiply both sides by the dx differentials. So I'm going to rearrange that as dy over g of y, okay, and equals f of x times dx. And so to make it clear, this is precisely on the left hand side 1 over g of y, but basically it's another function of y multiplied with the differential dy, and the right hand side will come out being f of x multiplied with the differential dx. And so at this point right here, that gives us our next step. We're going to take the integral side by side. We're going to take the integral side by side on this final equation right there. Okay, and then depending on how the equation looks, it's going to take us into different function, and we're going to algebraically rearrange our function to arrive at y equals some function, some unknown function of x. Now I have to use capital letter F here because I already used lowercase letter in our general guideline instruction. Okay, and then the step right here you will hear many textbook authors and you will hear many math professors refer to this steps right here where you were rearranging that so that all the y variables go one side and all of the x variables go on one side. This step right here is referred to as the step where we was separating, right, or separation of the variables. Okay, that was the step where we did the separation of variables. Okay, all right, and so now a little further and deeper insight about this example right here that I would like to point out before we close down this example 2 right here. All right, so right from example 2 right here as a problem that we solved the separable equation, a given separable differential equation. We came to the solution. For this equation, we came to the solution. Y equal, it was c1 e to the x plus 1 over 1 minus the c1, same c1 times e to the x. So I've been saying it, the c1 in the function, it's playing in the role as a coefficient. But in the end, it's just a value, it's just a constant that can change in value. We can assign different it can take different value. C1 can be different value. So let me point out, for example, when C1 equals a positive 1, our function here becomes y equals e to the x plus 1 over 1 minus e to the x. And so, ladies and gentlemen, this answer here, this specific solution will satisfy the equation. But also, if C1 equals a negative 2, for example, because I said earlier in the explanation of our work here, the C can be a coefficient that includes some negative sign as well. So if C1 equals negative 2, for instance, then the function like this becomes y equals now minus 2 e to the x plus 1 and over, but now it's 1 plus, because minus a negative 2 here, making it plus 2 e to the x. But so now I'm saying that this equation here specifically will also satisfy this separable equation. And so our point now is that we can have infinitely many solutions. It all depends on the different values given to C1 right here that we can find for C1. And so now back to just this solution that we have found previously. This solution that we found is rather or we refer to that as the general solution. It's not any one of these particular solutions, but it's a family, it's a whole family of solutions, which these two that I quickly pointed out right here is a member of. Okay, but it's now called the general solution to this separable equation right here. And to truthfully understand about it, it's a family of solutions where these two quick instances I point out right here are member of that general solution family right there. All right. All right, so now we're at example 3 of the lesson here. Okay, so the instruction of the lesson says let's solve the given DFQ right here, the given DFQ, the given differential equation, y prime equals y, given that y of 0 equals 1. So right now, let's put aside this information. I am not going to rush into understanding what that is yet. Let's put that aside. Let's say we put ourselves in a real situation right here, in a real-time situation. You see, and you read right here through the instruction. The instruction did not tell you to solve that as a separable equation, but it's us here being able to solve the equation by recognizing it as a separable equation is a tool, is an option now. Okay, so think about at the time being right here and solving this equation, there are many different methods, but if you can recognize this equation here as a separable equation, then we're gonna apply that method of how we solve that separable equation into solving this specific equation right here. Okay, and so that's why in real reality out there, no one's gonna tell you which method you're gonna use, but whichever you recognize about your equation, you're gonna go with that method. And so I pretend that right at this instance, y prime equals y. I'm seeing that as it's a product of y times 1, for example. Okay, so I'm seeing right here, it's some function of y, g of y. And like that one right here is some function of x, even though it's a simple constant function, f of x equals 1. So clearly I have recognized our equation given here is a separable equation, a separable differential equation. Okay, and so without worrying about any other methods that you will learn throughout the differential equations course right here with our ability to recognize this equation here as a separable equation, let's solve the equation as a separable equation using the method that we've learned specifically for separable equations. Okay. And then before I really start, I still haven't really tried to understand what this is yet. So let's put that aside for now. The equation y prime equals y. So now with the general guideline that we've learned, I'm going to let the left-hand side to be dy dx. That is the derivative notation. And that equals y on the right-hand side. Okay, but now further we're going to see this as a fraction of two differentials dy and dx. So we now have our choice to rearrange that. So I'm going to separate the variables. That's the next step here is the separation of the variables. So I am going to separate this as dy over y to equal dx, but namely this is 1 times dx. Okay, so at this point I have completed the separation of variables step right here. So now with our equation at this current point right here, let's even rewrite it a little bit to make it clear. It's 1 over y times dy to equal dx. All right, and so now the next step here is we're gonna integrate or take the integral both sides equally. Okay, all right, so the left-hand side here comes out being natural log of y. The right-hand side comes out being, because it's just 1 with the dx, so it's going to come out to simply x. They are equal. Technically, each side gets a plus c and a plus c, but we only need one overall plus c on one side. And commonly, we put that on the right-hand side. So now we arrive at natural log of y equals x plus c. All right, and so at this point right here, from algebra, now we know that the absolute value of y will equal to e to the x plus c. All right, and so at this point right here, I'm going to rewrite e to the x plus c as e to the c times e to the x. And that equals y in absolute value on the other side of the equation. And now the very similar arguments that I've made in example 2 right here, and we can carry that same experience here in this problem. Now y itself, now currently in absolute value, after removing the absolute value symbols, we're looking at y equal, truthfully speaking, plus or minus e to the c times e to the x. Okay, but now the way we're observing it doesn't matter what sign it is, plus or minus together with e to the c currently is still an unknown, so all of that here we can regard it to all of that as a c1 coefficient or a c1 constant, and the constant is playing in the role of a coefficient in this function. So yes, c1 can be either plus or minus the value of a constant value e to the c. Okay, and so in that case right here, now we can legally write our function here, y equals some c1 multiplied with e to the x. All right. And so as far as solving the equation, this equation that we have found right here, this solution that we have found right here, okay, is referred to as, and this is, think about if we doing this with some experience, with carrying over some experience from example 2 that we've done earlier, then this solution right now is regarded to as this is the general solution. Right. It's the general solution of our problem like that. Right. Y equals some coefficient. Could be positive, could be negative, equals e times e to the x. But so for this problem here, at this point, you got to think even further than that. So yes, the solution we have found, I wrote on the other board earlier, y equals some constant, c1, could be positive, could be negative, times e to the x, is only regarded as the general solution. Right. But now, how is this work related to this given information? The idea of the problem now is that at this point, again, our goal is to find the y function being an unknown function that satisfies the equation. But in this problem here, we want to find the unknown f of x equals y that satisfies the equation. We found a general solution, but not only that, we want to find the specific solution that meets this, that satisfies this equation, and further meets this requirements right here. The requirements here say that when x equals 0, okay, y value equals 1. See, this is the notation for saying, it's a shorthand notation indicating that y is a function of x. So the in parentheses here means when x equals 0, the y value equals 0. Right? So we want to find, because here is a whole family of solutions, a whole family of functions that can satisfy this equation. But now we want to find which specific one meets this requirement. Right? And so now in that way, from the given requirements, y of 0 equals 1. But from the general solution, according to the general solution we have found, again, let me write it down right here. Y equals c1 times some e to the x function. Okay? So with this general solution, then y sub 0 is consequently c1 that's still unknown times e to the 0. All right. And so now y of 0 is given to be equal 1 from the problem as the requirement. Y of 0, on the other hand, equals c1 times e to the 0 because I substituted x equals 0 into our general solution that we found. And so in this case here, at this point, we have our right to equate c1 with e sub 0 and make that equal 1 because these two are both equals to y of 0. Okay, and that's just my way of organizing the steps right there, and that's my way of presenting the steps, the reasoning, but you can also, at some point, you can cut down some minor steps like this. Okay, so at this point right here, e to the 0 is a 1, so that leads down to we have found specific value for c1. For c1, it equals to 1, because e to the 0 is a 1, so that means on the left-hand side we got c1 times 1. That's why I have just c1. That equals 1 as given. All right, so now c1 equals 1. We found a specific constant value. So now that brings down, that leads us down to now that general solution, y equals c1 times e to the x. Now it's just simply y equals e to the x because c1 equals 1. So we let down to that specific value. So ladies and gentlemen, this is the actual solution that meets the equation here. The equation y equals e to the x with c1 specifically equals 1. That equation, that function, that unknown function is now found, meets the equation, satisfies the equation, the differential equation, and further satisfies and further meets the requirements y of 0 equals 1. Okay, and so I'm still having the general solution here. Right? I'm still having the general solution here. That solution just now we have found y equals e to the x, one among the whole family of the general solutions here. This one is now referred to as, okay, this is precisely, we call that, it's the particular solution. All right. And so in the way how it is, it's always we have to find the general solution. And at that point, from that point on, we're going to find if the problem here gives a specific requirements, we're going to use that specific requirements right here to go ahead and go all the way down to finding the particular solution. So the solution here, the particular solution here is one member among the whole family of general solutions, and It satisfies the equation and it further meets the specific requirements. All right. All right. So in the end, at the very end of this problem right here, then allow me to give some generality about the problem here that we have specifically. Now, the problem here, what we had right here, the piece of information that I put in the highlighted red box right here is referred to as an initial condition. Okay? Because you have seen the process. We had to first find the general solution. And from that general solution, we're going to rely on this given initial condition to find our specific particular solution. The solution that meets this specific condition right here. Okay? And so that piece of information is called the initial condition. Because otherwise, without that initial conditions, we're not going to be able to have any particular solution. We're only going to end up with the general solution, which is a whole family of infinitely many solutions like that. And that they all differ by the value of this C1 constant. And then in the end, so the whole problem from the beginning that we found the general solutions and then routing ourselves down to finding the particular solutions based on the given initial condition. This entire problem right here is referred to as the initial value problem. All right, so the problem we have right here is one among the initial value problems out there. Okay, and then for differential equation experts out there, they call a problem like this the IVP for short. IVP. Okay, that stands for initial value problem. Okay.